Okay, this is lecture 4.1 for vector spaces and subspaces. The main definition I've already put up on the board because you don't want to waste 10 minutes watching me handwrite that. But you will want to have this. So either have your textbook open for reference or pause the video right now, write it down somewhere that you can quickly reference. This isn't the most important definition of this section. Ironically, it's going to be the next definition of subspace. That's going to be more important for this class, but we still need to know this. It has a lot of overlap with other properties that we've already talked about. So here it is. A vector space is a non-empty set V of objects called vectors, on which are defined two operations called addition and multiplication by scalars. And as we already know, scalars we also call just real numbers. Subject to the 10 axioms, or you can think of an axiom as basically just a rule or a property listed below. The axioms must hold for all vectors u, v, w in the vector space V, and for all scalars c and d. Okay, so this first one, a lot of these are going to be very familiar. So you already know most of these. That's the main thing. Few new ones. The first one, u plus v is in V. Okay, so what that's saying is if I have a vector u and I have a vector v, that I know both of those are in the vector space itself, then that means if I were to add them together, the resulting sum vector should also be itself an element of the vector space. So if I had a vector and another vector, I add them together with my addition operation, the resulting vector should be also in the vector space. The analogy that I've used before, it's not completely accurate, I don't think, but it kind of works. And you imagine like how families work. So if you have the father and you have the mother, if they have a kid, then that kid is also a part of the same family. Okay, so this is kind of don't take the analogy too far. But the idea is two objects in the vector space. If you make them interact with your operation, in this case the addition, then you should still end up with a vector that is in itself in the vector space. So this whole concept of having an operation where if you perform the operation and the result is still in the original kind of like set, we call this closure under whatever operation. So in this case, we're closing under addition because we're doing u plus v. So we would say that this property is that vector spaces, they are closed under addition. This is the only reason I spend a lot of time talking about that is because of how crucial closure is as a concept for this entire section, for the proofs that we're going to be doing in this section, things like that moving forward. The second one is familiar, so actually a bunch of these are. U plus v is v plus u. We know that's just the commutativity of addition. That u plus v in parentheses plus w is equal to u plus and then v plus w in parentheses. Okay, so being able to do it in any order, that's associativity of our addition. Property 4 here, right, we get there exists some element which we call the zero vector in our vector space V, such that u plus that zero vector just returns back u. In other words, there is an element in the vector space that if you make it interact with an operation, then you just return the same exact vector back. U plus zero vector is u. So the identity, essentially, for addition. Fifth one is that for all vectors u in my vector space V, then there is going to exist an element that we can call in general minus u in the vector space V, such that u plus minus u equals the zero vector. In other words, no matter what element I choose in the vector space, no matter what I choose, there is always going to exist in the vector space as well this element called minus u, where if I add then the u with this minus u element together, they return the identity, which is guaranteed to exist from the previous axiom. And returning to identity, that's what we mean by inverse. A lot of this stuff is generalized in abstract algebra. So if you ever, I'd strongly encourage you to to look forward into like group theory and things like that, because it's going to give even more general language for this, and then you'll realize that everything we've done in this class is really just an application, an example of an even higher abstraction of definition. Okay, the sixth one here, so we're going to start moving away from like the group theory stuff. This is the first 2, 3, 4, 5. This is like on a group theory, abelian groups. And moving on, we get to the actual stuff that makes this like vector field, vector space. So C, remember C is a scalar, C times U is in V. Okay, so now this is another type of closure statement like the first statement. This time I'm saying though, now a vector space is going to interact with the real numbers, some scalars. So if I take a vector from my vector space, and then I scale it with a scalar, then that resulting vector should also be a vector that is in the vector space. That shouldn't change its categorization. So if I take a vector and I scale that vector, then the resulting value or the resulting vector should also still be a member of the vector space. So we have a closure again. So it's the same concept abstractly as the first one. It's still a closure, but now instead of doing it with addition, what's the operation at play here? It's scalar multiplication. So we need closure or closed under scalar multiplication. Again, we'll talk way more about those closure statements in this lecture. So definitely stick around for that, because it's huge for the proofs, especially the subspace proofs. You'll see that closure with addition, closure with scalar multiplication, that tends to be the trickiest thing to do correctly and to understand, because it's the most abstract thing that you'll probably have done in mathematics this far. Okay, so 7, C scalar times then a sum of vectors equals V, we can distribute the vectors, right? So it's Cu plus Cv. We can also distribute the scalars. So if I have scalars C plus D, and then I multiply that by vector U, then I can distribute the scalars out to Cu plus Du. 9 here is kind of this. We've seen actually these ones before, all the way back, I think it was in the first chapter, when we did just properties of kind of vector arithmetic. C times du in parentheses, we could associate essentially with the scalar multiplication and do the CB first times u. And actually, yeah, a lot of this is pretty much just identical to the vector arithmetic properties that we've done. And then 1, this is new, so I think 1 times u is equal to u. So it's an identity for multiplication. Think of property 10 here being a parallel to the fourth one, where there was a 0 vector, so an element that if I used my addition operation, I would return back the same thing. And now with scalar multiplication, there is an element, that element is called 1, that if you multiply it by a vector, you would just return the same vector again. So we have identity for both. Notice that we have 2 operations. So for both operations, we need identities. So identity for addition is the 0 vector. Identity for scalar multiplication is the scalar 1. So there's our definition. So 10 axioms. That's a lot of properties. Okay, so when we're talking about vector spaces, we're talking about highly structured mathematical objects. Okay, that basically give us the rules for what we often consider to be the intuitive stuff in mathematics. So for all of the math you've ever done up until this point, whether you realize it or not, has essentially just been operating within the vector space, all the way up through pretty much. Yeah, even through Calc 1 and Calc 2, you're really operating just in the vector space of R. And sometimes you poke into some vector spaces of like functions, real valued functions. But now in linear algebra, we started poking into the vector spaces of like Rn, okay? And now we're gonna find out that that's not the only type of math you can do. So expand your, this is going to be a little bit challenging, because what you're going to have to do is separate out from your mind all of the things you've assumed about these common mathematical terms, and realize that there is a humongous world of abstraction that you've been previously unaware of. And so it's kind of getting a glimpse into this higher view of mathematics. It's very abstract stuff. And then what's crazy is that this isn't even the most abstract it can get. This is actually in itself an example, a shadow of higher algebra. So get used to a vector not necessarily just being your column vector. Now get used to a vector as a concept being the element of a vector space, where that vector space is going to be any set of objects, which we call the vectors, that satisfies all 10 of those axioms. So that doesn't need to be Rn. That doesn't need to be what we've been doing this entire time with chapters 1 through 3 of column vectors and such. These vectors could be a lot of different things. So I have a few examples, but I first want to just make clear at the top here that for all vectors u in V, and if I take a scalar in R, that implies that 0 times a vector u, the scalar 0 times a vector u, is going to give you the 0 vector. And then if I take a scalar and I multiply the scalar c by the 0 vector, I still return the 0 vector. And then lastly, you can think of minus u, the inverse for u in addition, as just being the scalar of -1 times the vector u. Okay, so that's kind of like a trivial, not trivial, but straightforward point and shoot confirmation that the inverse is always going to exist, because if you have a vector field where you're allowed to take all scalars, you can always take your vector u and always apply -1 to it. Okay, so like I was saying, the common example, what we've been doing all throughout chapters 1 through 3 is we just kind of assume the default state with the vector space of Rn. So this is going to be your vectors where we made x in R2 is going to be x1, x2. Or if I had some y vector in R4, then I had y1, y2, y3, y4 in a column vector like that. And so we were operating in these vector spaces. So R sub n, or not sub n, sorry, Rn is a vector space. And if you really think about it, all of the things we've been doing, most of these properties came from when we did the properties of vector arithmetic. So what that was doing was I was essentially establishing, hey, whether we knew it or not, because we hadn't gotten to this definition yet, we were clarifying that, yes, indeed, Rn is a vector space. Okay? Every single one of these properties, at some point, we've talked about, with regard to Rn, that it is true and that these things are things that we are allowed to do when we're doing algebra and arithmetic with vectors. Now, there are other types of vector spaces. So one of my favorite examples is this double struct P sub n, so P sub n, where n is greater than or equal to 0. This is the set of polynomials of degree at most n, and it consists of all polynomials of this form, right? P of t is equal to a naught plus a1t, a sub 2t squared, so on and so forth, where all of those t and the a naught through a naught, they're just real numbers, okay? And you might be thinking, okay, but Scott, a polynomial is not a vector, right? A polynomial is a function. A polynomial is a polynomial, right? That how on earth am I getting vector out of this terminology? We have to be careful. Again, just kind of forget what you've known about vector. Forget the things that you have assumed and associated with the word vector. And now start thinking about this term vector as an object, an element of a vector space. So if I have something that is a vector space, I have a set of objects that satisfies all 10 of these axioms, then any object contained within such a space we call a vector, irrespective of whether it's our conventional idea of what a vector should be, whether for an engineer that's like an arrow in space, or for a computer scientist, and we think of that as columns of data, essentially arrays. And even for the pure mathematicians who just think of the vector itself as this concept as an object of vector space, okay? So we need to move past the previously held assumptions and abstract, okay? So a polynomial can be a vector. And so that's why I'm denoting it with this p, with the vector symbol. I'm not putting that vector symbol there because I want to tell you that somehow the p is like some column vector with entries. No. But what I'm trying to communicate is that if I'm viewing up this polynomial p as an object, as an element of this overall set of all possible polynomials of, well, I misspelled degree, degree at most n, then yes, if this is itself, if we can show that this set, p double struct the pn, is a vector space, then any polynomial that is in that set we can call a vector of the vector space Pn. okay? So I know it's going to take a while for if it feels weird, it feels hard to understand, that's okay, because it is kind of weird and it is hard to understand. So give yourself time, give yourself the time to wrestle with these definitions, to push your brain to abstract this a little bit, okay? So like, I don't know if I'll go through every single one of these properties, but we can definitely show. So, for example, u plus v in v. So if I have two polynomials of at most degree n, and I add them together, will I result with another polynomial that is also at most degree n? Well, yes, right? If I took, I'll call this one p1 is equal to a naught plus a1t plus a2t squared plus so on and so forth up until a sub n t to the n. So this is one such element contained in here. And I need to define another one, so I'll define p sub 2. Again, these are vectors, that's why I'm denoting it with a vector. This is going to be the polynomial, I just need to use different constants here. So b naught plus b1t plus b2t squared, and so on and so forth until I get to b sub n t to the n. So here I have p1 and p2. So what I would say is clearly p1 and p2 are members of p sub n, okay? They are vectors of this vector space. And so I gotta show, is it true that their sum is also in there? Because that's a necessary property. It has to be closed under addition. So let's take a look. If I do p sub 1 plus p sub 2, this needs to be also in p sub n. So if I do this sum and it ends up being an element that's not, then we violate the property, and this is not in fact a vector space. But we'll find out that now I have a naught plus a1t plus a sub 2t squared plus so on and so forth, a sub n t to the n. So that is p1 plus, and then p2 is b naught plus b1t plus b2t squared all the way up to the b sub n t to the n. And we see we can just put all like terms together. So this is going to be a naught plus b naught, and then plus a1 plus b1 times t, and then all the t squareds together. So a2 plus b2 t squared, so on and so forth, and I can group the a sub n and the b sub n together for t to the n. So when I look at this, and I know that all of those coefficients are just other scalar values, then yes, this element itself is a polynomial of, at most, degree n. That is, this is an element, this is itself a vector described by p1 plus p2 that is, definitionally satisfying what it takes to be in p sub n. So I find that p1, p2 being vectors in this vector space results in their sum also being in the vector space. So it satisfies closure under addition, the first axiom of a vector space. And so you can kind of verify all of these. Intuitively, think about this p1 and this p2. If I did the sum p1 plus p2, but then flipped the order and then did p2 first plus p1, does that change the overall sum? No, of course not, because when we look how it simplifies down, we know that regular addition with scalars commutes, so it's not going to change anything. So check, that works. Associativity, if I added a third one, does it matter which order we do it? It's all addition, all the coefficients are still just real addition, so that's not going to change. Is there a zero vector? What does the zero vector look like in a vector space that's made out of polynomials? Well, it's going to be specifically the polynomial where every single coefficient is 0, right? 0 itself is a polynomial. So my identity I guess I could call the identity maybe like p sub 0, for example. So the identity p sub 0 can function as my 0 vector. So if I want this to be the 0 vector, maybe I'll write it like this to kind of tie in the concept. So my 0 vector for p sub n is going to be the polynomial p sub 0, which is 0 plus 0t plus 0t squared all the way to 0t to the n, or simply just 0. Because now, if I use this 0 vector and add it to any, so now say I take this 0 vector and I add it to p1, then what I'm doing is I'm taking this polynomial and adding this polynomial to it. Well, that's just adding 0. It's just not going to change anything. So this is just going to return to me my p1, and that'll always happen. So hopefully these few examples of checking with these axioms is helpful, okay? Because this is showing that we can think of other objects that don't even remotely resemble visually what we might intuitively think is a vector to begin with, but definitionally, it's satisfying this definition, vector space with vector, okay? I think I'll show, I'm not going to show all of the rest of these properties, but I do want to show at least one that involves like the scalar distribution stuff. Like so, for example, this c times u plus v, okay? So now say I take a constant, and so I have some constant c in R. And so is it true that if I take c times p1 plus p2, is that the same thing as doing that constant times the first polynomial plus the constant times the second polynomial? Well, intuition says obviously yes, and we can show that. Because that's going to be c times their sum. So a naught plus a1t plus a sub 2t squared plus all the way through a sub n t to the n plus b naught plus b1t plus b2t squared all the way out to b sub n t to the n. And then, so that's our c times p1 plus p2. And basically, I know from distributive property, I can just put that c and multiply it against every single one of these, right? So I could just do c times the a naught plus a1t plus a2t squared plus a sub n t to the n, because I know all of those are scalars. So I distribute to the first parentheses, and now I distribute to the second, plus c times b naught plus b1t plus b sub 2t squared, so on and so forth, b sub n t to the n. But this is just what we mean by the vector p1, so c p1, and that's just the vector p2. So it does distribute. Okay, so this is what we mean. If you can define a set, if you can define some sort of set of objects where its elements, we call them vectors as a means of terminology according to this definition, so long as all of those vectors within this defined set of objects satisfies all 10 of those axioms, then you have a vector space. So that's pretty cool. Even though this doesn't look initially like a vector, so long as you put it in the correct vector space, then yeah, in that context, it is a vector. So, again, I know it's probably a little bit abstract right now. It's a little challenging. So give it time, think about it, practice with it, review. And doing the proofs is going to help with the subspaces, I think. There's another common example. It's basically the set. If I take the set of all real valued functions on a specific domain, then all of those functions become then the objects of this overall set. And then we can call the function itself a vector of this vector space, which is the set of vectors that are all defined on a specific domain. Okay, so, and the reason why we can do that is because, again, you can show that all 10 of those properties hold. So, if you want to give that a look in the textbook, you can. I do want to move forward. with the next definition. And actually, I think I should put this definition on the other side so that I can keep it up. So, last chance, get this written down, make sure you have it, you want to know it. But the next definition is going to be like far more, I think, important for this class specifically. Okay, definition. A subspace. A subspace of a vector space let's call it V, is a subset H of V that has three properties. That has three properties. The following three properties are going to be remarkably important for the section and honestly just a lot of things moving forward. First one, the zero vector of the original vector space V is also in our subspace. So we cannot have a subspace if we don't have that identity, basically. B, H, so the subspace, is closed, there's this closure again, under vector addition. Okay, so in math terms, this is going to be really helpful for proofwriting. That is, there's a keyword, that is really helpful to reframe something used in English to then say it with its logically equivalent math stuff. U, given vectors U and V in the subset, in the subspace H, that implies that their sum is also in H. So taking U and V in H immediately directly implies that the sum U plus V is also in H. So that's what we mean by closed under vector addition. And then C is basically we just need closure under the other operation. Because remember, the definition of vector space had two operations, addition and scalar multiplication. So it should be no surprise that we want our subspace to also be closed under both. H is closed under scalar multiplication. That is, so again, we reframe this in terms of this, the math notation that's going to be most helpful for proofwriting. If I take a vector U in H and some scalar, then that directly implies that taking the scalar and multiplying it by the vector should also produce a vector within H. And here's just kind of like this definition is not as important, but it's good to know the terminology if you see it. The set consisting of only the zero vector in a vector space V vector space V of V. So if I wanted like a trivial subspace, you can just take the zero vector out of your original vector space and isolate it as a single subset, and boom, you technically have a subspace. But it's not very interesting, and it's called the zero subspace. Zero subspace, intuitively, and is denoted basically with just set notation, right? We have a subset, and it contains the zero vector, and that's it. Okay, so not as important of an idea. Biggest one is definitely this one right here. You're going to want to have that memorized by heart. Okay, so because the key theme that's going to be moving forward is then we start asking the question in this chapter, like, what constitute, like, how can we show something is a subspace of a vector space? Can I do that? What if I'm trying to prove that something is or is not a subspace of a vector space? Then I should have a little mental checklist of what I'm actually trying to prove. Okay, so the first thing that gets missed a lot is that, notice in the definition, a subspace of a vector space V is a subset. This is a big word that people will forget in their proofs. Subset. So, for example, this should be intuitive. If you don't even take a subset of your original vector space, how on earth are you expecting that to be a subspace if it's not even a subset of your thing? So, you might think that R2 is a subspace of R3, but no, it's not. R2 is not a subspace of, say, for example, R3. Okay? You might be thinking, well, but R2, 2 is smaller than 3, so sure, that seems intuitive, that seems right. No, because this is not even a subset of R3. When you really think about it, objects in R2 are objects of the form x1, x2. That's an entirely different element. That's an entirely different object than objects general of the form x1, x2, x3. Okay? So make sure you check this, because some questions will give you something that looks like it could intuitively be a subspace, but it itself is not even a subset of your vector space. So check that. When you're given a vector space and then you're given another set, make sure that set, and just verify, usually just by observation, that set is itself a subset of the original vector space. So I would, if I was asked to prove whether or not R2 is a subspace of R3, the proof is easy. I would say, well, observe that R2 isn't even a subset of R3. Hence, it can't be a subspace. Being a subspace is like an even higher level of specificity than being a subset. Being a subset alone, that fails. And so if it's failing that lower condition, of course it's not going to be definitionally a subspace. So be mindful of that. Don't forget that in your proofs. And I'll emphasize that again when we do examples of proofs on this. Okay, so you're always going to want to check that you actually have a subset. Then you're going to want to check that the zero vector is in your set. That's usually just done by a pretty straightforward computation. And then you show your closure. And so you're going to learn how to construct these proofs where you define two vectors and then add them together and then show that their sum is itself a vector in the thing. And then similar with the scalar multiplication. Okay? So that's your checklist. Four things to do in a proof. Verify, firstly, that you even have a subset in the first place. Because if you don't even have a subset in the first place, what are you doing? The second thing is now the zero vector. So make sure you can actually find a way that the zero vector is in your subspace. The third thing, do closure for addition. Then lastly, do closure for scalar multiplication. Those four things always have to be done if you're going to fully prove that something is in fact a subspace of a vector space. If at any point any of these fail, congratulations, you've also finished the proof to prove that it's not a subspace. So it goes both ways. Okay, so let's actually just get into it now and do a proof. Yeah, let's just get into it and do a proof. Okay. So I'm actually honestly going to leave this up here for reference because it's going to be helpful. But what I will do is I'll erase this definition and put the theorem that we'll prove, and then we'll use that entire side for the proof itself. So I'll take this down. So if there's any definition that you really should memorize and learn by heart and practice, it's this one. That's a huge one. Okay, here's the theorem. Let V1 to Vp be vectors in V, which is itself a vector space. Just some proof writing language here. Whenever you're given let stuff in something, and then there's no verb and it just goes V, a vector space, what that's simply stating is that this object V is a vector space. That's probably self-intuitive, but in case it's not immediately obvious, that's what that means. It's not saying that the elements are a vector space. It's saying that these are elements. It's kind of initializing elements in something and declaring what that thing is all in one line. Okay. So we have vectors V1 through Vp in a vector space called V. Then we want to show that then the span V1 to Vp is a subspace of the original vector space. What I'm going to do is I'm going to ask that if you do not remember the definition of span, to stop watching this right now, pause it, get your definition of span, remember the definition of span, write it down, have it to reference, because if you don't have the definition of span internalized as a concept, then the proof is just not going to make sense. As any proof with span isn't going to make sense if you don't know the definition. So review that. It's worth your time to spend reviewing the definition so that the logic of the proof makes sense. Faking it is a terrible way to make it in this case, okay? So don't do that. Review this definition. If you don't have it in memory, seriously, just pause this. It's a video. Technology's awesome, okay? Review that definition, find that definition, and then come back. So any type of subspace proof, like I just said, needs 4 components. The first component being that we need to, for sure, confirm that the thing that we're talking about is itself a subset. Then we need the 0 vector. We need closure of addition. We need closure of scalar multiplication. And so that's why I've left this up here, because that's kind of hard to remember if you don't have something to reference. Okay, so it's all going to be up here. Let's first initialize our stuff. So in our theorem, we need some vectors, we need a V, a vector space, and we need span. Okay, so let V1 to Vp and V a vector space. A vector space. Okay, so the task here is we want to show that the span of these elements is a subspace of V. Okay? So what I'm going to do is I'm going to use a that is keyword So here's keyword let. Another keyword I want to show. So that is, I'm going to articulate this. That is, we want to show that the span V1 through VP satisfies the definition of subspace. And what does it mean to satisfy the definition of subspace? It means to satisfy the definition of the subspace. Okay. For convenience, because if I have to write out span of V1 to VP every single time I want to refer to the span, that's going to get really obnoxious. So we're just going to quickly relabel it to H. So every time we talk about H, we're really talking about the span, okay? But notationally, it's just going to be much easier to write. So for convenience, and this is a common proof technique, especially for things that make it more readable. So for convenience, that's technically a term you can use if you want to make a substitution of a long string of something to shorten it for reference. Let, so then there's an initializing word, let H be used to refer to our span from now on. And if I want to be really clear to my reader who is trying to follow my logic here, I'll just specify that that's for this proof in this. Because who knows? If you do two consecutive proofs and you want to reuse H for something else, then it's good to specify that this has kind of just been locally defined to satisfy in this proof alone. Okay. You don't have to do that, but again, this is just good form if you ever want to do higher math studies or write papers and things like that. Okay. Now we can observe. So when I was talking about the subset thing, you don't have to do too much. I think its importance is the fact that it's easy to forget. So just don't forget to make the observation. So you can say, and this is very much allowed in this case, because of the way span is defined. Span is defined as basically these linear combinations. So yes, of course, your linear combinations are going to be in there. So we, this is a good word you could use, observe. We observe that H is a subset of V. In other words, I'm not talking about some like random set of other objects that isn't even definitionally what I mean by my set of vectors V, okay? I have vectors, they're in terms of those very elements of those vectors. So by vector properties, yes, I have a subset. I don't know, it's not all of them, we don't know that for sure, but it is, that's why I have the inclusive subset, just in case. So all this is saying is that we're good to go. We're clear to launch, you're clear to take off, and you can now go check all of these three axioms without worrying that you've forgotten something important at the beginning, okay? Let's see, we may proceed to the three subspace, subspace axioms. So now, I'm transitioning the focus of the proof to shooting one of these down, one by one, okay? So, I'll kind of, because I know I'm going to need to erase the board, I'll keep track of my items like this. So, I'll go for axiom, the first axiom, so axiom A in this case. So for axiom A. Okay. The first axiom is that, so notice what I'm doing. I'm articulating what I'm trying to show. What is the first axiom in the first place? Well, it's that the zero vector of V is in H, okay? So is that zero vector is in H. Okay, so if that's what the first axiom is, and I'm trying to show that H does satisfy this, then that is basically what I'm trying to show. So we show, or we see that I can just take 0 times V1 plus through and through to 0 times Vp, which is just the zero vector. Okay, so fantastic. How did I know I was allowed to do that? Well, because remember, H, this entire time, every single time you see an H, I basically shortcutted writing out the entire span of V1 through Vp, okay? And if we recall what the definition of span is, I'm gonna just put it over here. Recall that the span of V1 through Vp, span is a set of all possible linear combinations. All possible linear combinations. So C1 V1 plus etc. to CP VP, where C1 through CP can be any combinations of real numbers. Okay, so all possible combinations. So if I just select my C weights to be all 0 in a span, well then of course I get the zero vector. So we've seen that this zero vector is in fact in H. So I can conclude that this axiom is satisfied. So I've done what I need to show. I've articulated what I was trying to show. I showed it by understanding the definition of span of my subspace, and then I basically let the reader know, okay, cool, so check. Now we can move safely on to the next one. So then axiom B. The second axiom is that, and it's over there on the other whiteboard, is that H is closed under addition. Alright, that's what this says. H is closed under vector addition. That is, keyword, so I'm linking this to now some math that I can operate with. If I took a vector, I'll use x and y. So if I had a vector x and a vector y in H, that should directly imply that their sum, x plus y, is also in H. So thus, our task in this part of the proof is, okay, well, how do we do it? How do I show this statement? Okay, how do I come up, what constitutes a good way to mathematically, rigorously show this? Well, that's what I'm going to kind of articulate here for us. Our task in this part of the proof is to, we need to declare what we mean by x and y in the first place. So is to declare it's kind of like you can't code without, well, you can't run a program if it doesn't have code. You can't do a computation in a calculator without some sort of input. Well, you can't do a proof of a statement without any objects. So let's declare some vectors x and y, and obviously I want them to be in H because that's on the starting thing. and show that their sum x plus y, right, must also be in H. Fair enough, right? So in order to show closure being that x, y, and H implies that x plus y and H, then the task is basically, let's declare some vectors x and y, and then after I've declared those vectors x and y, show that if I add those vectors together, that the resulting vector is in itself satisfying what it means to be in H. Okay, so let's see if I can fit this on the bottom here. I'm not going to be able to. So what I'm going to do is I'm going to erase, sorry, there's x and b. So I'll pick up, I'll erase this, but keep this, have this written down. So pause right now if you haven't finished writing this down. Write it down. And then once you've got it written down, resume, because I'm going to erase this and then actually do that part. So this is axiom B. We're still on axiom B continued. So I'll put, okay. So we're still on the axiom B. So we had just articulated the problem and now we're going to do it. So let's initialize our stuff. Let x and y be vectors in H. Okay, so what does that mean then? So there was my initialization. Then, by definition, recall that H is just standing in so that I don't have to rewrite span of V1 through Vp every single time, right? So what then can I talk about X? I can talk about X if it's in H, that is, if X is in the span of these vectors V1 through Vp, that means it is some linear combination. It is some linear combination of vectors V1 through Vp. So X is some linear combination A1 V1 plus through AP Vp of those vectors. And then that means Y is also just some linear combination. B1, V1 plus BP, VP, where we want to specify to be definitionally sound that A1 to AP and also my B1 to BP, they are just scalars, right? So I'm making sure I'm careful to not to keep all of my definitional stuff intact. X is some linear combination, Y is a linear combination, and those weights, A1 through AP and B1 through BP, they're just scalars. So we satisfy the definition of span, because that's what H is, okay? So great, we have X and Y. We've initialized it. We've represented it according to its definition, so the task was to add it together, right? And show that that sum is also in the thing, in H. So, what's my chart here? Okay, yeah. So we show that. If I take X plus Y, then that's equal to A1 V1 plus all the way down to AP VP, and then plus the Y, so B1 V1 plus all the way down to BP VP. Now, we can rearrange this to be all of the, so combine like terms, A1 v1 plus b1 v1 is going to be a1 plus b1 v1. And that's going to go all the way down to AP plus BP times VP. So, since, take a look at this. This is just only a combination again, because A1 plus B1, every single one of those constants is just another arbitrary scalar. So since I can write it this way, AI plus BI is also just a scalar amount for all of the i's that start at 1, 2, and go up to p, right? I'll just put 1 through p. Right? So all this notation is saying is that AI plus BI is a scalar for all of the i's 1 through p. So like, if I was equal to 1, then this would be A1 plus B1. Then I goes to 2, so A2 plus B2 is also just a scalar. For 3, A3 plus B3 is also just a scalar. Up to P, AP plus BP is just a scalar. So that's all of these coefficients in the sum, which satisfies the very definition of span, or not span, but being a member of span. This is a linear combination. So then, since this is true, then just by definition, we've shown that x plus y is definitionally in the span, which we have been denoting as h. Okay, so recall, I'll just put here for a second, recall that h is being used in place of span v1 through vp. Okay, so it's in the span. Okay, so we've shown that's a great phrase to use to summarize like a subsection of a proof. We have shown that the subset H, which is the span, is closed under addition, which is precisely what the second axiom is here. So great. We were able to show that if I have x and y in H, then their sum is in H, which means that this H subset is closed under the addition operation. Okay, so there's one more axiom. Okay, so basically a similar, I spent a lot of time explaining the first closure proof to really have a feel for what's going on. So now that you have a feel for what's going on, I can say this. A similar argument is made for the third axiom. Third axiom. So what is the third axiom? The third axiom is that H is closed under scalar multiplication. Okay. So that is, let's frame the jargon being closed under scalar multiplication. That's jargon, that's math vocabulary. Let's frame that with math terms. That is, if I have a vector u in H and a scalar c and r, having those two things should directly apply that c times u is also in H. Okay? So again, very, very similar stuff. To a similar argument is going to be made. I need to initialize my stuff, and then once I've initialized it, I'm going to show basically through computation that the CU is an H. Very similar to the previous one. So initializing, so let U in H and C in R. Might feel a little bit redundant that I'm saying this so many times. Obviously, the more experience you get with proofwriting, the more streamlined they can become. But I would rather you understand the underworkings of the logic, the undercurrents of logic that are happening in a proof, and understand that, because once you really understand that, then you can appropriately abbreviate and shorten and make more succinct your proofs. If I start with just advanced proofwriting, you have no idea. There's a lot of assumptions that are just going to happen, and I don't want you to be filling in wrong reasoning to make up for the gaps that are not being explained to you, okay? So if you don't write it exactly like this, that's fine, so long as it's logically true, so long as it logically follows, and that there's no holes in the argument. Okay, so let U in H, C in R. Okay, well then, I can talk about my vector U. Again, U is an H, and don't forget that, recall that H is just what we've been using shorthand for the span here. So that means U is some linear combination of these vectors. So I can just do, I guess I use the C here. So just as a notational convention, I'm not going to use C1 to P because I'm already using C here, so I'll just move to the D. So D1. As much as possible, I don't want to be having ambiguous or overlapping variable usage in a proof. It's bad form. So U is equal to D1 V1 plus blah, 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 right? This linear combination where, and I need to clarify that these D1 through DP, I introduced something to the proof, so I need to clarify what they are. The D1 through DP are scalars. Okay. Okay. Then, okay, so we can just show. So we show that the task here is now to multiply the constant C with my vector U. So let's just do that. C times U is equal to C times the vector U. So D1 V1 plus blah, 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 plus DP VP. And then if I multiply this out, I get C times D1 times V1. And that'll distribute all the way out, and I end up with CP times DP, or sorry, C, the constant C, times DP times the vector VP. And again, since each scaled di, so C times di, so that's CD1, CD2, CDP, etc., right? So CDI is just another constant for all I that starts at 1 goes to P. Then C times U is itself just another linear combination of the vectors of V1 through Vp. To be another combination, a linear combination means it's just in the span. Okay, so it is in the span H, which we've been calling it. Okay, so then great, we've shown the third axiom. So thus, we have shown that H satisfies all, that's key, all necessary conditions and axioms to be a subspace of V. That is, H, which is the span of V1 to VP, is a subspace. Of V. Okay, it's a lot of math. That's a lot of good math. So yeah, make sure you can do that proof. Make sure you understand the proof. And when you think that you understand the logic of it, you think you understand, then I have a little challenge for you. So here's your chance to pause and get your notes before I erase. I'm going to give one practice problem. So if you want to kind of see if you can do it and if you understand it, then here I'll give you this. As something to practice on. Let V1 and V2 be in V a vector space. Prove that H equals span of V1, V2 is a subspace of V directly. Okay, what do I mean by directly? I just mean, because there is a logical caveat. You could prove this by simply saying, hey, we proved the general version from V1 through VP, ergo, set P is equal to 2, and it holds. So don't do that. Okay, this is supposed to be an example to help you practice the whole proof directly. So that's what I mean by directly. To start from, declaring V1, V2, and V, to start by declaring the span, go through the definition, go through all three axioms, make sure you know how to show all of that on your own. Okay, with your own creativity, with your own use of notation, your own words, your own logic. So there's that to practice if you want a chance to actually practice. Okay, I know that's a lot. This is a really long lecture, unfortunately, but it's very important. There's a lot of material to cover, and especially that proof. I really wanted time to go over that proof. So if you have any questions, obviously let me know in class. And I'll see you Monday.